Chapter 12 serves as a great introduction to random events and to simple probabilities. So let's first look at random phenomena. We've spoken before about random phenomena, and we had said that if an event is considered to be random if we know what the outcomes are that could occur, but we don't know which particular value will happen. So remember, when I flip a coin, I could get heads, I could get tails. I know those are the outcomes, but I don't know which one I'm going to get when I flip a coin. Same thing with rolling a die or drawing a card, etc. So we're going to begin to look at probability, and there is experimental probability and theoretical probability, and they are both obviously probabilities but computed a little bit differently. So the experimental probability is the long-run relative frequency. So this is based on actual data. So if I flipped a coin 3 times and I got heads, tails, heads, my experimental probability would be that I'd get heads 2/3 of the time, and tails I would get 1/3 of the time. Obviously, we're looking at a long-run relative frequency. We want to do this many more times than 3, so 3,000, 300,000, 3 million, etc. Every time I flip a coin, that is called a trial. Every trial has an outcome, heads, tails, etc. All of the outcomes combine to make events. If I were to list all of the possible outcomes, that is called the sample space. So again, if I'm flipping a coin, the sample space would be the set that includes heads and tails. Independence, this is one of the most important things that as soon as you understand this, it will just make the rest of chapters 12 and 13 go much more easily for you. So if we're talking about independent trials, what I need is the outcome of one trial doesn't influence the outcome of another. So let's take a look at the difference between the two. If I flip a coin, theoretically, and we'll talk about theoretically in just a moment, but we think that we're going to get heads 50% of the time, and we're going to get tails 50% of the time. And if I flip a coin and get heads, then the next time I flip a coin, I still have 50% heads and 50% tails. So whatever I had the first time doesn't affect what happened the next time. So let's instead look at a bag of marbles. And so I'm not going to draw the bag, but I'll draw some marbles for us to take a look at. So here I have 8 marbles. I've got 3 orange, 3 yellow, and 2 blue. And if I were to draw a marble out of the bag, then my probability of red is 3 out of 8, and probability of blue is 2 out of 8, which I could reduce to 1/4. And my probability of yellow is 3 out of 8. Now let's assume that I have drawn a marble and it was red. What is now the probability that I draw a red? Well, there are 1, 2, 3, 4, 5, 6, 7 marbles left in the bag, and there are only 2 reds. And for blues, there's still 2 blues, but again, there's only 7 in the bag. There's still 3 yellows, but there's only 7 in the bag. So notice these probabilities are not the same, so this would not be independent, assuming that, of course, that I didn't put the marble back in the bag. So again, the theoretical probability, and again, we're going to talk much more about all of this in the slides to come. This is just a good introduction. Theoretical probability is the probability of each event in the sample space occurring, and it's not based on data, but instead based on probability theory. So these probabilities that I came up with here, that was theoretical, based on the fact that there were 8 marbles and 3 were red, or here, based on the fact that there's 2 sides of a coin, and one of those 2 sides is heads. Before we start computing any probabilities, I feel it's important to sort of further explore the experimental probability versus the theoretical probability. So sometimes we don't know what the theoretical probability is. So if I said, what's the probability that I get a green light when I come to a certain intersection, I don't know unless perhaps I go talk to the people who time the lights. So instead, what we can look at is we can look at, remember we said before, the long run relative frequency, which means what's the probability over the long run. So this is a great example of that. Let's say I get to the intersection, day one, I get a green light. Yay for me, 1 out of 1 time I got a green light. So notice I've put a point here at 100%. The next day, unfortunately, I get a red. That's sad. But out of the 2 days that I stopped, only one of them was red. So 1 divided by 2 is 50%, so notice my next dot is at 50%. The next day I get a green, so that's 2 greens out of 3 total times I've stopped at the light, which is 67%, and notice that's where my next dot is. And we continue and continue and continue. So assume I did this 100 times, and I want you to notice what's happening here is it's sort of leveling out to about this line. So it looks to be about 30%. And again, that's a lot easier if I had, lines on my graph, but you get the idea. So we're looking over 100 days. So this is called the law of large numbers. The law of large numbers states that the long run relative frequency of a repeated independent event, again independent because what I got on the first day, green, red, yellow, etc., doesn't affect what I would get the next time I stop at the light. And what it's saying is that it eventually is going to settle down to the true probability or theoretical probability. So again, and it looks like I went with 35 instead of 30, but we get the idea that what we're looking at is that it's settling down to a certain value. So as we can see from the graph, it continues to get closer and closer and closer and closer to some number. Now if I did this 1,000 times, then they would be much more dotted together, a little bit less variation, again because the sample size is large. So obviously that's the point, which is the law of large numbers, means as n gets bigger, as the number of trials gets bigger, our probability is going to settle into the true probability. There is also a phenomenon in statistics known as the law of averages, and I've given you 2 examples here to illustrate what the law of averages means. So I have 9 beautiful nephews, which is absolutely true. If a sister-in-law of mine were to get pregnant, then I would certainly have a niece because I'm due a niece. So what are your thoughts on that? Or if I've flipped a coin 10 times and gotten tails each time, then I'm surely going to flip a heads the next time because I'm due flipping a heads. So this way of thinking is actually called the law of averages, and it is absolutely false. There is no law of averages, or you can say there is a law of averages, but it's completely false. So essentially what it's saying is it's not taking into account that every time a sister-in-law of mine has a baby, it's an independent event. Each time I have a niece or nephew, I have a 50% shot of getting a girl and a 50% shot of getting a boy, theoretically. We won't get into all of the biology and etc., etc. Same thing with a coin, a little bit easier to look at. So I'm flipping a coin. I know each time I'm going to get heads 50% of the time. I'm going to get tails 50% of the time. So even if I flipped a coin 10 times and I got tails each and every time, on my next flip I still have a 50-50 shot. So again, law of averages is false because it doesn't take into account that these are independent events.